Hello! Today we are going to be introducing some basic operations with binary relations. So let's suppose that we have A and B, two non-empty sets. And let R from A to B be a binary relation. Right, we already know that what this means is that R is a subset, a non-empty subset of A Cartesian product B. And well, the two first operations that we are going to introduce are the restriction of a binary relation and the inverse of a binary relation. Is that okay? So what is going to be a restriction of a binary relation? So let's suppose now that we are considering A hat a subset of A and B hat a subset of B. All right, so the restriction are restricted to, and we are going to use this symbol here, restricted to A hat Cartesian product B hat is gonna be a binary relation from A to B. All right. Given by the following rule: a pair A, B is in R restricted to A hat Cartesian product B hat if and only if this little a belongs to A hat and the second component, little b, belongs to B hat. That means, let's suppose that we have this relation described extension. So what we are going to do if we want to compute this restriction here. So we are going to go over all pairs in the relation and we are going to verify whether the first component of that pair is in the subset A hat and also the second component of the pair is in B hat. If both conditions are satisfied, we are going to keep, or we are going to include that pair in the restriction. If at least one of these two conditions fails to be satisfied, so if either the first component is not in A hat or the second component is not in B hat, we are going to discard that pair. Is that okay? Obviously, the restriction are restricted to A hat Cartesian product B hat is a binary relation. It's a binary relation if and only if at least one of the pairs in R remains in the restriction. So if that restriction is different from the empty set. Is that okay? Good. Okay, let's suppose that we have a subset A hat of the set A and a subset B hat of the set B. And let R, we are gonna use this symbol here. With A hat Cartesian product B hat as a sub-index of this symbol, and this symbol here is a vertical harpoon. Be the set whose elements are all pairs A, B in R such that the first component is in A hat and the second component is in B hat. Is that okay? If this set is different from the empty set, then it is a binary relation from A hat to B hat, which is called the restriction of R to A hat Cartesian product B hat. Is that okay? So notice that we are including here the case in which A hat is equal to A, and also the case in which B hat is equal to B. So obviously if both A hat is equal to A and B hat is equal to B, there is not any restriction here. The restriction is going to be the same binary relation R. But well, something that we do sometimes is we use a subset for a proper subset for A hat, but we keep B hat equal to B. So that means in this case we are just restricting the set for the first component, or we restrict just the set for the second component. Is that okay? In this case, in many cases, instead of writing R restricted to A Cartesian product B hat, we just write R restricted to A hat if we are keeping B. Invariant, if we are keeping A invariant, we write this. Okay, we have the following. We have if R is a binary relation from A to B, and A hat is a subset of A, B hat is a subset of B, the restriction of this binary relation to A hat Cartesian product B hat is the set whose elements are all pairs in the original binary relation such that the first component is in the subset A hat, and at the same time the second component is in the subset B hat. And this is going to be a binary relation as long as it is different from the empty set. That's the only. All right. So let's see a very simple example. In this case, we have that I is the set with these 5 elements. B is the set with these 5 elements, the first 5 natural numbers. And we have a binary relation R from A to B, also containing containing 6 pairs. All right. A hat is a subset of A, consisting of these two elements, the first and the last one. And B hat is a subset of B consisting of these three elements, 2, 4, and 5. And now we need to find what is going to be the restriction of R to the Cartesian product of this A hat and B hat. So let's see, can you help us with this example, please?
So to find the restriction of the relation R with Cartesian product A hat, B hat, we have to find all the pairs in the relation R for which the first component is included in A hat and the second component is included in B hat. So we check the first pair. The first component is included in A hat, but the second component is not included in B hat. Therefore, the first pair cannot be in the restriction. Let's check the second one. The first component is included in A hat, and the second component is included in B hat. So that pair belongs to the restriction. The third pair, the first component is not in A hat, so automatically we can discard that one. Same for this pair. Let's check this one now. Well, the triangle is not included here, so it cannot be in the restriction. And the last one, the first component is in A hat, and the second component is in B hat, so therefore it also has to be in the restriction. Just to summarize, we have to check to find the restriction of relation R. We have to check that both conditions needs to be satisfied. The first component of the pair has to be included in the first set, and the second component of the pair has to be included in the second set. When we look at relation R here, the first component is in the first set, but the second one does not belong to B hat, so we can discard that one. Then, as we already saw, this one belongs since both conditions are satisfied. For these next three, all three of them were discarded because the first condition that the first component is included in A hat is not true, so that failed. And for the last one, both conditions were also satisfied, so it is included in the restriction.
It's a little bit more sophisticated example. So now we have a binary relation R from the set of natural numbers. To the set of natural numbers. So in this case, A is equal B equals to the set of natural numbers. Remember that we are starting at 1, so 1, 2, 3, 4, and so on. All right. And so now we are not describing this binary relation extensionally as we did before. So by extension, I mean that I'm listing all the pairs or the elements in the binary relation. Now what we are doing is describing this binary relation intentionally. So we are providing a property that only the pairs in our binary relation satisfy. And that property is this one. So n, comma m is gonna be a pair in this relation if m, the second component, is the smallest multiple of n that is greater than n. Is that okay? So the second component must be a multiple of n, but at the same time greater than n. And out of those multiples that are greater than n, we are choosing the smallest one. Is that okay? All right. So, for example, is 3, 7 a pair of this relation? Well, let's see if that the given condition is satisfied. So, in this case, n is equal 3 and m is equal 7. So, m is the smallest multiple of n. So, in particular, n must be a multiple of 3, but 3 does not divide 7. So, no. The condition is not satisfied. Is that okay? But what about 3 sets? Is 3 sets in this relation? Well, now n is 3 and m is 6. m is equal to 2 times 3. So yes, m in this case is a multiple of 3. M is greater than 3. So 6 is greater than 3. Okay? And there is not other multiple of 3. Which are the multiple of 3? 3 times 1, that is 3. 3 times 2, that is 6. 3 times 3, that is 9. So there is not other multiple of 3 that is greater than 3 and less than 6. So 6 is the smallest multiple of 3 that is greater than 3. So yes, this is a pair of the relation. It's okay? So now you know how this property is working. Alright? And well, we are not restricting the set of first components, so A hat is equal to A in this case, but we are restricting the set for the second components. B is the set of natural numbers, but now B hat is only including those natural numbers that are multiples of 4. Is that okay? So we need again to find the restriction. Alright? So come on, help us with this.
Okay, to solve this exercise, the first thing I'll do is passing from the given intentional representation of R to an extensional representation. Why? Because I think it's going to help me. Okay? So to start, what's a multiple of n? So a multiple of n is a natural number that is obtained by multiplying n by other natural number. For instance, we can multiply n by 1, we can multiply n by 2, we can multiply n by 3, and we can keep going so on by any natural number.
All those are going to be multiples of A.
Exactly. So, but let's look, because we have a restriction in the per m, nm. So it says that m is the smallest multiple of n greater than n. So let's look at the first example that we have, the first natural number that we have. So n times 1.
The first multiple that we have.
N times 1 would be n. In this case, n will be equals n. And right here, if we focus on this word, it says that it has to be greater than n. So let's look at the second pair right now. The second pair is n times 2. So we have twice n. So we keep it. The first multiple of n we discarded because we saw that it was the same. Let's see what happens with 3. When we multiply n times 3, we obtain 3 times n. 3 times n. So it's just in one part, it's good. It's good because it's 3 times n is greater than n. But at the same time, we need the smallest multiple of n.
That is greater than n.
That is greater than n. And in this case, we already have that multiple, which is 2n.
Because 3 times n is greater than n, but it's also greater than 2n. So these two are multiples of n. Both of them are greater than n, but this one is smaller than this one. And if we continue multiplying n by 4, n by 5, we are going to continue getting multiples of n that are greater than n, but also greater than this multiple here. Which means that the smallest multiple of n out of all those multiples that are greater than n is 2 times n. Is that okay? So in how many pairs n is going to appear as the first component?
Exactly 1.
In exactly 1. Yes or no? And what is going to be the second component of that pair? So the smallest multiple of n greater than n. That multiple is going to be 2 times n. So how can you describe now? What is going to be your... so this is the formula also for
yes.
m. That means that n is the only second component that we have for that n is going to be 2 times n.
Yes.
Okay?
Okay, so the extensional representation of the relation will be n, the pair n, and then m will be 2 times n. For n belongs to the natural numbers.
All right.
let's go now to the restriction, because this is the relation, but we're looking for the restriction. If we go to A doesn't have a restriction, so A is free. A is all the natural numbers starting at 1. But B, in this case, we do have a restriction in B. And it says, let B be the set of all multiple of 4s. Okay, so this has to be a multiple of 4.
And what about the first component?
The first component is any natural number.
A natural number, because A hat is the set of natural numbers. This means that we don't have any problem with any first component. Okay, the first component can be any natural number, but the second component has to be a multiple of 4. Is that okay? Okay, so what we have? First component can be any natural number, but the second component has to be twice that first component, because we have reached the conclusion that the smallest multiple of n that is greater than n is twice that n. Yes or no?
Yes.
All right. Now, if we are computing the restriction, what we need? No problem with the first component, but the second component must be a multiple of 4.
Yes.
But already that second component is even. So it's 2 times something.
Yes.
But we need that second component to be 4 times something. So to get this as a multiple of 4, what do we need?
We need 2 as a factor of n.
So we need 2 dividing n, because if we can factor 2 out of n with this other 2 that we have, we are going to get the 4 that we need. For example, what happens if n is 7? If n is 7, what is going to be that pair? 7, 14, which we can write as 7, 2 times 7. So do you think that this pair is going to be in the restriction?
No.
No, because this is not a multiple of 4. And this is not a multiple of 4 because 2 is not a factor of n. Yes or no?
Yes.
But if you have, let's say, 10, n equals 10. n equals 10, that means that the pair is 10, 20. Which we can write as 10, according to its formula, 10 times 2 times 10. But now, this is a multiple of 4 because we can get 2 as a factor of n. And that 2, with the 2 that we already have, is going to give us the 4 that we need. Mm-hmm. Yes or no? We can write this as 2 times 2 times 5, because 10 is 2 times 5. And combining these two 2's, we are going to get the 4 that we need. Yes or no?
Yes.
So what is this telling us?
We need n to be an even number.
To be an even number. Yes or no? Yes. And this is telling us now that what is going to be the restriction. So if n is going to be even, we need n even to get here a multiple of 4. That means that the restriction of this binary relation to A Cartesian product, to A hat Cartesian product B hat is going to be. So n has to be even, so let's say 2k. Now this 2 times n becomes 2 times 2k, which is going to give us the multiple of 4 that we need. And k is any natural number. Is that okay? And this is going to be the restriction in this case. All right? Summarizing what we have. The first thing that we did was converting this sentence here, this condition here, into formula. Yes or no? So how do we get the multiples of n? Since the second component must be a multiple of n, or a multiple of n with additional characteristics, but well, multiple of n means that we need to multiply n by another number. In general, we can use 0, we can use negative, but since we are working here with a set of natural numbers, we don't use those numbers. So n times 1, n times 2, n times 3, n times 4, and so on. All right? These are all the multiples of n. This means that n has infinitely many multiples. This one is exactly n. This 2 is 2n. This is 3n. Okay? So this is not greater than n as we need. The greater than n are all of these. But this is the smallest one out of all those that are greater than n. So that means that n is gonna appear as the first component in exactly one pair, and the second component of that pair is gonna be twice n, which means that R can be extensionally described as n to n, because we have concluded that 2n is the smallest multiple greater than n, where n is any natural number. Okay? So, what we need now is to get the restriction of R to the Cartesian product of the set of natural numbers and the set of multiples of 4. But, well, the first component are not restricted, because the first component in the original relation is the set of natural numbers. A hat is exactly the set of natural numbers, so we don't have any restriction, at least not imposed by the subset A hat for the first component. We don't have any restriction for the first component, but the second component has to be a multiple of 4. For this to be a multiple of 4, since this is already even, what we need is a 2, one more factor. Okay? So we need to get 2 as a factor of n. But if 2 is a factor of n, that means that n must be even. Okay? If n is even, this is going to be multiple of 4. If this is a multiple of 4, n must be even. Is it okay? So this means that the restriction is going to be n even, so n is equal to 2 times some k, natural k, and now this is going to be 2 times 2k, which is 4k, and k is a natural number. Is that okay? So this is the restriction in this case. All right? All right. So what is going to be the inverse now? We have again R, a binary relation from A to B. Okay? The set, which we are gonna denote this way, the same R but with an exponent -1, whose elements are all pairs BA in B Cartesian product A, such that the pair AB is in R, okay, is a binary relation from B to A, and it is called the inverse of R. Okay, so the inverse is a binary relation from B to A, which are the pairs that we have in the inverse. All pairs BA in B Cartesian product A, such that if we switch the components, the pair AB is in R. So if you want, pragmatically what we are doing is we are going over all pairs in R, switching the two components. Okay? Every time we switch the two components of a pair in R, we put the resulting pair in the inverse, and when we are done with all the pairs, that's gonna be R to -1. So okay? All right, let's see an example. Right, we have this, that is the definition of the inverse. Let's compute the inverse of the last binary relation, the last example that we considered before. So remember that we have R, this is an example, from the set of natural numbers to the set of natural numbers. Okay? given by, so the pair n is in this relation if and only if m is equal to 2 times n, that's okay, which enables us to write R as n comma, as the set whose pairs are n comma 2n, which n any natural. Is that okay? So what is gonna be? This means that the first component is any natural number, but the corresponding second component is gonna be even. It's gonna be twice the first component. So what is gonna be the inverse in this case? Well, basically what we need to do is to switch the pairs. All right, let's see one more example. An easy one, just to make sure that everything is clear. So now we have A. A is the set whose elements are these three faces. B is the set whose elements are coffee and pastelito. So we have the relation R from A to B consisting of only three pairs. Is that okay? We can suppose that this pair means that we like coffee, this we don't like pastelito, and this we are indifferent to coffee. Is that okay? What is gonna be the inverse in this case? Well, in this case it's pretty easy. The inverse is gonna be now from B to A. All right, and the only thing that we need to do is to switch the components of every pair. So now if we switch the components of the first pair, we are gonna get coffee, happy face. If we switch the components of the second pair, we are gonna get pastelito, sad face, and the same for the third pair. All right, and this is gonna be the inverse in this case. Is that good? The last operation that we are gonna see is the composition of binary relations. So let R from A to B and R hat from B to C be binary relations. Right? So obviously A, B, and C are non-empty sets, and notice that the set for second components of the relation R is the same as the set of first components for the relation R hat. So, okay? The set, and I will use this notation here, R hat, a little circle here, R, whose elements are all pairs A, C in A Cartesian product C. So it's like B serving as a link for A and C, for which there is B, an element B in B, such that AB is in R and BC is in R hat, is called the composition, or let me put it this way, R composite R hat. And we are going to write it and read it in the opposite order as we write in this notation. So we are going to mention the relation to the right first and the relation to the left second. Okay? So notice what is this telling us. Which are the pairs that we are putting here? we have A, we have B, and the first relation is relating elements in A to elements in B. We have also C, and the second relation is relating elements in B to elements in C. What is this relation doing? Well, in the case that is a relation, which means that that has to be different from the empty set. For an element A to be related to an element C, what is this telling us? An element A is going to be related to an element C if we can find B such that A is related to B and B is related to C. It's okay? So in this relation, we have two different relations from A to B, from B to C. If we want to relate now the elements in A to the elements in C. How we are going to do it? We are going to do it the following way. We are going to say that these two elements, one in A and another in C, are going to be related if we can find B that is common to these two, such that the element in A is related to that B and that B is also related to C. That's the only way we are going to be relating A and C according to its relation. So if there is a B that is connecting these two elements, is that okay? So it's like A is a friend of B, B is a friend of C, and A is gonna be a friend of C. Is that kind of idea? Is that okay? And well, our composite R hat is gonna be a binary relation from A to C as long as it is different from the empty set. Okay, and let's see a couple of examples, and I think this notion is gonna be clear. Okay, this is the definition then. So we have a binary relation R from A to B, another binary relation R hat from B to C, these two, the same set here, and the R composite R hat is the set whose pairs are in A Cartesian product C, but A, C is a pair. In this set is we can find B in the set B such that this A with the B that we are finding is forming a pair in the relation R, and the same B with this C is forming a pair in the relation R hat. Is that okay? So, and as long as this is different from the empty set, in that case, this is gonna be a binary relation from A to C. Okay? So let's see an example. So we have these three sets. R is a binary relation from A to B. Happy face 1, comma 1 is the first pair. Happy face, comma 2 is the second pair. Sad face, comma 2 is the third pair, and that's it. And now R hat is gonna be from B to C, and we are gonna have 1 alphas, the first pair, 1 betas, the second pair, 2 gamma, 2 alpha. All right, this is R hat. So what is gonna be the composite binary relation now? R composite R hat. Well, look at the following. according to this, to the relation R, happy face is related to 1. But 1 is related to alpha, so 1 is serving as a link for happy face and alpha. So if we choose B equal 1, is that okay? And A equals happy face and C equals alpha, B, that in this case is 1, is serving as a link for happy face and alpha. So it's telling us that happy face alpha is a pair in the composite binary relation. But 1 is also related to beta, so 1 is also serving as a link for happy face and beta. So the pair happy face beta is also a pair of the composite binary relation. If we look at this second pair here of the relation R, this is telling us that happy face is related to 2. Since happy face is related to 2, and according to the second relation, 2 is related to gamma, 2 is serving as a link for happy face and gamma. So the pair happy face gamma is also a pair in the composite binary relation. Is that okay? Well, 2 is also related to alpha, which is telling us that 2 is serving as a link for happy face and alpha, but we already have that with 1, so we don't need to repeat it. Is that good? Okay. Alright, so that means that according to the composite relation, happy face is related to all the elements in C. Good. That is not necessarily happening for all the elements in A, but in this case it's happening. So what about the sad face? Sad face according to R is just related to 2, but 2 according to R hat is related to gamma, which is telling us that sad face is related to gamma. But also sad face is related to alpha, because sad face is related to 2 according to R, and 2 is related to alpha according to R hat, so this is giving us this pair. But is sad face related to beta? No, because for sad face to be related to beta, according to the composite relation, we need to find someone in B such that sad face is related to that element and that element is related to beta. But the only element related to beta, according to the relation R hat, is 1. And 1 is not the second component for any pair having sad face as the first component. So sad face is not related to 1 according to R, and 1 is the only element related to beta according to R hat. So there is no link between sad face and beta. So sad face is not related to beta in the composite binary relation. Is that good? So this is gonna be all pairs in the composite binary relation, and that's what. Notice that the composition is pretty natural, even though the formal definition can be a little bit confusing, but it's recreating what happens in a factory. So let's suppose that we have 2 machines. First machine R, if you want, you can think of a function, and you know what is the meaning of that the pair AB is, if we think of the relation as a machine. Well, that means that when we put A inside the machine, the output is gonna be B. That's what this means. Is that okay? And let's suppose now that we put another machine behind the first one. So R hat. So notice A enters in R. R is processing A to get a B, but we don't see that B. B is getting now inside the second machine R hat to produce a C. So that means if we only look at the second machine, that the pair BC is in the second machine R. But since we are not seeing this B, and we look at this as a whole, now A is related to C. So AC is a pair not of this machine, but of this more sophisticated machine that is the concatenation of the two machines. So the second machine after the first ones, which is what we are calling the composite binary relation. So in this case, I'm not entering in those details if every A is related to more than one B or something like that. I'm just explaining the basic connection between A and C using an element in B that we don't see. Is that okay? All right. So in the case of a function, we have the notation. Remember that AC if A comma C is a pair of, we look at this composition as a function, this binary relation is a function, we can describe this process here as, well, we are evaluating this function RA, all right? This input is taken by R, and the output that R produces is gonna be taken by R hat. That's what is happening here. So R evaluated at A is B, and that B, that is the output of the first function, is going to be taken as an input by R hat, which produces the final output C. That is what is happening here. Is that okay? And another important thing here that is not only for functions, this is valid for any binary relation, is that this operation is not commutative, so this is not equal to R hat composite R. Indeed, this can be possible and this can be not. So notice the following. If you think of machines, maybe the outputs of the first machines are valid inputs for the second machine, but if we invert the order of the machines, what this second machine produces is not a valid output for the first. So formally, remember that what we are doing is R goes from A to B, R hat goes from B to C, which means that what R produces, or the second components for R, add first components for R hat, or what R produces is valid, is a valid input for R hat. But if we switch the order, that means that C must be at least a subset of A, which in general is not necessarily the case. Yes or no? Okay? In general, it's not the case. All right? So, again, this operation is not commutative. The composition is in a certain order. Can be possible. The other composition can be impossible, and even in the case that the two are possible, not necessarily they are gonna be equal. Is that good? So let me put an example. Okay. Well, the last example that we saw before, R composite R hat was possible. That was the one that we did. But you can realize that, well, A was the set happy face sad face. So A was the set happy face, sad face, this indifferent face. B was the set whose elements were 1 and 2, and C was the set whose elements are alpha, beta, and gamma. Is that okay? And R was from A to B, R hat from B to C. So this composition is good. We can do it, and indeed we did it. Is that okay? But this composition is not possible. Is that okay? Well, why? Because now the pairs here are gonna be an element in B and an element in C. But the second component here must be the same first component of a pair here to be able to connect this one to the first component here to the second here. But the pairs here, the first component is in A and the second component is in B. So the second here with the first here never match because these two sets have nothing in common. It's okay? So this is an example in which the composition in certain order is possible, but in the opposite order it is not. Okay? All right. But what happens if I use C now equals to A and I consider new relations? From A to B, okay, and R hat from B to A. Well, say that R, in R we have the pairs happy face 1, sad face 1, indifferent face 2, and in R hat we have the pairs 1 indifferent phase, 2 happy phase. All right. Oh, notice now that R composite R hat goes from A to B, from B to A, so from A to A. And R hat composite R, well, this goes from B to A, and now this one from A to B, so this goes from B to B. So these are complete different binary relations. The first one goes from A to A, the second one goes from B to B. Which are going to be the pairs in this one? Well, happy face is connected to 1 according to R. Now 1 is connected to indifferent face according to R hat, which is telling us that happy face indifferent face is a pair in R composite R hat. 1 is not connected to any other element in A, so, and happy face is not connected to any other element in B, so that's it with happy face. Now sad face is connected to 1, 1 is connected to indifferent face, so this is also producing sad face, indifferent face. And finally, indifferent face is connected to 2, 2 is connected to happy face, which is producing the pair indifferent face, happy face. And this is the composition R composite R hat. However, R hat composite R is gonna be 1 is connected to indifferent face, and indifferent face is connected to 2, so 1 is gonna be connected to 2. This is serving as a link. 1, 2. Indifferent face is not connected to any other element in B, so this is all that we can get from this pair. Now 2 is connected to happy face is connected to 1, so we get that 2 is connected to 1. And that's it. So notice that these two relations are different. Is that okay? Alright, last class we studied 3 properties to classify binary relations, so fully defined, injective, and surjective. So we are going to conclude this lecture today by introducing this theorem that is proving that those properties are preserved on their composition. So let R from A to B and R hat from B to C be binary relations obviously we are assuming here that A, B, and C are non-empty sets. The first result here is going to be the following. If R and R hat are fully defined, okay, then R composite R hat is fully defined as well. Okay? All right. Okay, let me prove this one. All right, what we need to prove is that, so notice the following. This R composite R hat is okay, is from A to C. All right. So what we need to prove is not only that this is a binary relation, but that every A, every letter A, every element A in A is the first component of at least one pair in R composite R hat. Yes or no? So let's take any element A in A. Let's fix one element in A. What do we know? We know that R is fully defined. Since R is fully defined, this element A has to be the first component of at least one pair in the relation R. So this means, since R is fully defined, there is an element B in B such that AB is a pair in R. But now we are going to look at this element B. And B is an element in the set B, so first components for the relation R hat, which is also fully defined. So since R hat is fully defined, this element B that we found, that is the second component for this A in the relation R, is the first component of some pair in R hat. So there is an element C in C such that BC is in R hat. But this B is the same. This B is the same. If this B is the same, B is serving as a link, as a connection for A and C. Therefore, AC is in R composite R hat, which means now that this A that we have fixed, which is arbitrary, is also the first component of a pair in this composition. So every element in A is also the first component of at least one pair in the composition, and the result is proven. Well, the second one is if R and R hat are injective, okay, then R composite R hat is injective as well. Obviously, we are supposing here that this composition is a binary relation. The case that is empty, there is nothing to do. It's trivial. Okay, but it's not a binary relation, so we cannot apply the definition. All right, so what we can do here? So let's suppose that there are two pairs with the same second component. Is that okay? There are two pairs in R composite R hat with the same second component. All right? So we have AC and A prime C both in R composite R hat. But if this is a pair in the composition, I want to continue here. If AC is in R composite R hat, there is B in B such that AC is in R and BC is in R hat. Is that okay? Okay. Sorry, AB is in R and BC is in R hat. Okay? Same thing if A prime C is in the composition R composite R hat. Now we can say that there is, let's say B prime, because it's not necessarily this one, in B, such that A prime B prime is in R and B prime C is in R. Okay? In R hat. Is that okay? But now we look at these two. We look at these two pairs. What these two pairs have in common? So these are two pairs in R hat with the same second component. But R hat is injective, which means that we don't repeat second components. So that for every element in C, there is at most one element in B, okay, that is related to that C. But here we have two, B and B prime. Well, but we haven't said that those two are different. Since it's at most one, those two must be the same. So since R hat is injective, B must be equal to B prime. Is that okay? But if B is equal to B prime, these two pairs that we have here, then we have AB in R and A prime B prime, but B is equal to B prime, so A prime B also in R. But R is also injective. If R is also injective, we cannot have repeated second components, which is telling us we cannot have two pairs, have different pairs having B as the second component. So A must be equal to A prime. So since R is injective, okay, A is equal to A prime. Yes, sir? Well, but if A is equal to A prime, if A is equal to A prime, these two pairs are not different, which is telling us the only way we can have the same second component in two pairs is if the first components are also equal, which means that these two pairs are basically the same pair. You see? So we don't have repeated second components, and this relation here is gonna be also injective. Now what we have, the third one is that if R and R prime are surjective, then R composite R hat is surjective as well. Okay? Well, basically what we need to prove now is that every element in C is the second component of at least one pair in this composition. Yes or no? So prove, let letter C be any element in C. Is it okay? Since R hat is surjective, this C is the second component of at least one pair in R hat. So there is B in B such that the pair BC is in R hat. And now we look at this letter B that we found as the first component for this pair. Letter B is in B and R, so B is the set of second components for R, and R is surjective. Okay? So there is, this letter B is the second component of at least one pair in R. So there is an element A in the set A such that AB is in R. But this is the same B. So AB, BC, B serving as a link for A and C. Therefore, AC is in R composite, R hat, which means now that for every C elements, letter C in the set C, we can find an element A in the set A such that AC is a pair in the composite relation. So this means that every element C in C is the second component of at least one pair in this composite relation, and the composite relation is going to be also surjective. Is that okay? So there is one more property that I didn't mention before, but it's one of the most important cases. That is the case of function. It's okay? I'm going to leave it as an exercise to you, proving that the composition of two binary relations that are functions is indeed a function. Is pretty similar to the proof. So if you understand, or if you understood the proof that we did before, so it shouldn't be too hard to construct the proof by yourself for the fact that the composition of two functions is also a function. Okay? And another thing that I wanted you to think about is, well, what happens if instead of the composition, we consider the other operations that we studied today? The restriction and the inverse. Is that okay? And we are going to talk about that in another lecture. So thank you so much.